Welcome to this video from a series about probability theory. The question on the screen might sound stupid to you, but counting is a very important concept for probability theory. In the last video, we covered naive probabilities, which were computed by counting possible outcomes of a random experiment. For a simpler example, such as the example of 3 separate coin flips, it was still possible to enumerate them by hand. But what about more complex cases? This is where combinatorics come in handy to determine the number of outcomes of an experiment. In this video, we will cover the two fundamental concepts, sampling with and without replacement, and I will show you how to intuitively derive the formulas such that you don't need to memorize them anymore. Then, we will go into a very famous probability theory example, the birthday problem, which you will be able to solve using the methods that we have covered so far. The basis for everything that will follow is the multiplication rule. Consider an experiment which consists of 2 sub-experiments. Each of the sub-experiments has 4 different outcomes. What would be the overall number of possible outcomes? Think about it for a moment and maybe pause the video. You can determine the outcomes by multiplication of the number of possibilities in each sub-experiment. This can be explained by the fact that for each outcome of the first experiment, you can have all 4 outcomes of the second one, so in total 4 times 4 outcomes. We will now illustrate this concept using a visual illustration and a more concrete example. You want to buy ice cream and have to first decide between a cake cone or a waffle cone. Then, there are 3 different kinds of ice cream: strawberry, lemon, or apple. How many possible outcomes of this scenario exist? We can draw a tree for this setting. First, we have 2 possibilities, for each of which there are additional 3. Using the multiplication rule gives us 2 times 3, which is 6 different outcomes in total. Be aware that the order in which you make the decisions does not matter for the number of outcomes. If we swap the tree order, we still get the same result. Now that we know of the multiplication rule, we can directly derive sampling with replacement. Sampling with replacement means that we have n objects to choose from, and after picking one, we put it back such that it is possible to get it again. This is repeated k times and also called sampling. The multiplication rule directly gives us n to the power of k possible outcomes for this experiment, since in each stage it is possible to choose from n objects and the stages are repeated k times. Let's illustrate this at an example. We have a box with 3 balls in it. Thus, n is equal to 3. For k equal to 1, so 1 sample, we get 3 different outcomes. If we repeat this sub-experiment twice, making k equal to 2, the possible outcomes become 9. In sampling without replacement, the objects are not put back after sampling. Again, we have n, which stands for the number of objects to choose from, and k is the number of samples we obtain. To illustrate the concept, we take a look at a box with 5 balls in it. In the first sub-experiment, we have 5 possible balls to choose from. Then, in the second sub-experiment, there are only 4 left, since 1 has already been picked. This can of course be repeated in the same fashion. For k being 3, we would get 5 times 4 times 3 possible outcomes of this scenario. We can write this down in a more general fashion, using n, which was our number of objects. Then, we can also include k, such that we are able to later derive an even more general formula that holds for all n and k. We see that we start at n possibilities and reduce it k times. Of course, it is not possible to pick more than n objects, so k is limited to n. There exists a nice closed formula for the possibilities in sampling without replacement, which is given by the factorial of n divided by the factorial of n minus k. We will see why this is the case in the next part. For sampling without replacement, we want a closed formula which gives us this expression. Remember that the factorial of n is given by the multiplication of all numbers up to n, which can be written like this. If we compare this to what we want to obtain, we can see that the first multipliers are not needed, which means that we need to eliminate them somehow. This can be achieved by reducing this fraction. The part that is not needed is exactly n minus k factorial, since it contains all multipliers from 1 to n minus k. This gives us exactly the term that we want in a nice closed form, which is n factorial divided by n minus k factorial. You can use this to obtain the possible number of outcomes of a counting experiment without replacement for n objects and k samples. As promised, we will now take a look at the birthday problem, a very famous probability theory example. Here, we can immediately make use of sampling and counting, as well as the basics from the last video. In this scenario, we have k people in a room, which is the number of samples we take. Can you guess what the probability for one birthday match is? We assume that all days are equally likely, that the birthdays are independent, so there are no twins, and that there are 365 days in a year. N is equal to the number of days. You can imagine it as follows. Each person is one sample for the possible days in the year. We sample with replacement, since it needs to be possible that two people sample the same day. To compute a naive probability for this, it would be necessary to count the different cases in which at least one match happens, but this also includes the cases in which there are 2, 3, or more matches. Divided by the number of total outcomes, given by the sampling with replacement formula from the multiplication rule, is the probability for a match. This is a very tedious task, but there exists an easier way of computing this probability. Think back to set theory and sampling without replacement. Maybe you are able to reformulate this probability using the complement and then solve it by sampling without replacement. If we compute the complement of the probability for a birthday match in a room, this gives us 1 minus the probability of no match. The naive probability of no match is determined by sampling without replacement. Think about it in the following way. You ask the first person in the room about a birthday. There is no chance that you get a match, since there is only one birthday. This corresponds to k equal to 1. Then you ask the second person. You only get no match if their birthday falls on another day, so you only have 365 minus 1 possibilities left. This goes on until you reach 366 people. At that point, the probability for no match is 0. One can visualize this probability over k. Interestingly, after 23 people in a room, the probability for a match is already at 50%. After 57 people, it already reaches 99%. This example shows very nicely that in probability theory it is very important to think about the alternative description of sets and being able to handle counting experiments such as we have seen using the rules from sampling with and without replacement. If you want to learn more about the fundamentals of probability theory, you can watch my other videos from this playlist. Thanks for watching, and I hope you learned something from this video.